Now let's look at centrifugal pumps and some of the things that affect their operation. The discharge pressure of a centrifugal pump is directly proportional to the specific gravity of the liquid being pumped. When the specific gravity of the liquid being pumped increases, the discharge pressure increases. When the specific gravity decreases, the discharge pressure decreases. Suppose a centrifugal pump has a discharge pressure of 160 psig when pumping kerosene, specific gravity 0.8. Then if it were to pump water, specific gravity 1.0 at the same rate, the discharge pressure would be greater than 160 psig. To calculate the value of this higher discharge pressure, simply multiply the kerosene discharge pressure times the specific gravity of water divided by the specific gravity of kerosene. 160 times 1.0 divided by 0.8 equals 200 psig. Here's another example. Suppose this same pump were to pump a light naphtha, specific gravity 0.7. Then the discharge pressure would be less than when pumping kerosene, specific gravity 0.8. To calculate the value of this lower discharge pressure, simply multiply the kerosene discharge pressure times the specific gravity of light naphtha, divided by the specific gravity of kerosene. The light naphtha discharge pressure equals 160 times 0.7 divided by 0.8, or 140 psig. To repeat, the discharge pressure of a centrifugal pump is directly proportional to the specific gravity of the liquid being pumped. When the discharge pressure for water, specific gravity 1.0, is 200 psig, for kerosene, specific gravity 0.8, it is 160 psig, and for light naphtha, specific gravity 0.7, it is 140 psig. Now let's calculate the head in feet that a centrifugal pump will put up by using the formula head, feet, equals the pressure divided by the product of 0.433 times the specific gravity. We will use the same liquids in these calculations as we used in the specific gravity and discharge pressure correlations: water, kerosene, light naphtha. What is the head in feet a centrifugal pump will put up when pumping water, specific gravity 1.0, if the discharge pressure is 200 psig? In the formula, H equals P divided by the product of 0.433 times specific gravity. Substitute 200 for P and 1.0 for specific gravity. Solving, we get 462 feet. Now, what would be the head if this same centrifugal pump were pumping kerosene, specific gravity 0.8, if the discharge pressure were 160 psig? Again in the formula, H equals P divided by the product of 0.433 times specific gravity. Substitute 160 for P and 0.8 for specific gravity. Solving, we get 462 feet for the second time. Now let's make a third calculation for the light naphtha. In the formula, H equals P divided by the product of 0.433 times specific gravity. Substitute 140 for P and 0.7 for specific gravity. Solving, we get 462 feet for the third time. These calculations show that a centrifugal pump will put up the same head in feet regardless of the specific gravity of the liquid being pumped. To repeat, centrifugal pumps have the same discharge heads for any liquid, but discharge pressures are directly proportional to the specific gravities of the liquid. And positive displacement pumps have the same discharge pressure for any liquid, but discharge heads are inversely proportional to the specific gravities of the liquid. Now open workbook number 2 to exercise 11. We usually abbreviate pump terms. SH for suction head, minus SH for suction lift, DH for discharge head, TH for total head, and NPSH for net positive suction head. Now let's look at some other pump terms that you must know. Brake horsepower, liquid horsepower, efficiency, and pump capacity. Brake horsepower is the power required to drive a pump at a particular set of conditions. Brake horsepower is power input. The brake horsepower required increases with increasing capacity. It takes more horsepower for the same pump to pump 200 gallons per minute than it does to pump 100 gallons per minute. Liquid horsepower is the rate of work on the liquid being pumped. Liquid horsepower is power output. The liquid horsepower output is always less than the brake horsepower input because of power losses in the pump. The efficiency of a pump equals the liquid horsepower output divided by the brake horsepower input. Since you must always put more power into a pump than you get out of it, the efficiency is always less than 100%. Pump capacity is usually expressed as gallons per minute. It can also be expressed as gallons per hour, gallons per day, barrels per hour, and barrels per day. Now open workbook number 2 to exercise 12. Now we're going to review pump characteristic curves. These curves tell us how a particular pump will operate under various conditions. Let's make one again. First, let's develop the total head versus capacity curve. The vertical scale on this chart shows total head in feet. The horizontal scale shows the pump capacity in gallons per minute. The amount of total head a pump produces will be different for different capacities. This pump produces 175 feet of total head at 0 gallons per minute. These data are represented by this large dot. At 100 gallons per minute, the pump produces 165 feet of total head. These data are represented by this second dot. At 200 gallons per minute, the pump produces about 150 feet of total head. Now we have a third dot. If we continue to mark additional points and then connect them with a line, it will look like this. Now we can find the head produced for any capacity. Let's try it. Suppose we want to find the total head at 350 gallons per minute. We simply find 350 gallons per minute on the capacity scale, move straight up to the curve, then move across to the total head scale. Our answer is about 110 feet of total head. Usually you will see characteristic curves shown in this manner. Several different characteristics are shown on the same chart. The horizontal scale shows capacity only. There are several vertical scales, a different one for each characteristic curve. This one shows efficiency and goes with the efficiency curve. This one shows horsepower and goes with the horsepower curve. This scale shows total head and goes with the total head curve. And this one shows net positive suction head and goes with the net positive suction head curve. Now open workbook number 2 to exercise 13.